Today I'm diving into the world of classical physics, the backbone of our understanding of the physical universe. Buckle up because we're going on a journey from Newton to Maxwell. First stop, Sir Isaac Newton. You've probably heard of his 3 laws of motion. These laws explain how objects move and interact. The first law, also known as the law of inertia, tells us that an object will stay at rest or move in a straight line unless acted upon by an external force. The second law gives us the famous equation F equals ma force equals mass times acceleration. And the third law, for every action there's an equal and opposite reaction. Together these laws laid the foundation for classical mechanics. But Newton didn't stop there. His law of universal gravitation explained how every mass attracts every other mass. Imagine you're pulling on the Earth and the Earth is pulling on you. That's gravity at work. Next, let's jump to classical electrodynamics with James Clerk Maxwell. Maxwell's equations are a set of 4 fundamental laws that describe electromagnetism. They explain how electric and magnetic fields interact and propagate through space. Ever wondered how light travels? Maxwell's equations tell us that light is an electromagnetic wave. Now, classical mechanics and electrodynamics are just part of the story. Classical thermodynamics, for instance, deals with heat and energy. Think about how your coffee cools down over time. That's thermodynamics in action. And don't forget about classical chaos theory and nonlinear dynamics. These fields study how small changes can lead to drastically different outcomes. Ever heard of the butterfly effect? That's chaos theory. Classical physics might sound old school, but it's the bedrock of modern science. Modern physics is a term that often refers to the groundbreaking theories and discoveries of the 20th and 21st centuries, including quantum theory and relativity. Classical physics does an excellent job of describing systems that are larger than atoms and molecules. From the macroscopic objects we interact with daily to astronomical phenomena, classical mechanics provides a framework that is both intuitive and accurate. However, as we delve into the atomic and subatomic realms, the laws of classical physics begin to falter. This is where quantum physics steps in. Unlike classical physics, which is deterministic, quantum physics introduces probabilities and uncertainties. At these tiny scales, particles behave in ways that defy classical logic. The famous double-slit experiment, for example, reveals the wave-particle duality of electrons, something classical physics cannot explain. Classical electrodynamics governed by Maxwell's equations also needs modifications when dealing with extremely small or weak electromagnetic fields. Quantum electrodynamics provides these corrections, ensuring the accuracy of predictions at all scales. Relativity, both special and general, further distinguishes modern physics from its classical counterpart. Classical theories assume absolute time and space, but relativity teaches us that time can dilate and space can curve, especially near massive bodies or at high velocities. These effects are imperceptible in our everyday experiences but become significant when dealing with high-speed particles or cosmic phenomena. Interestingly, the bridge between classical and quantum physics is an active area of research. The correspondence principle suggests that as systems increase in size or mass, their behavior increasingly aligns with classical predictions. This is why we can often ignore quantum effects in our daily lives, even though they are always present at a fundamental level. In this segment, we'll delve into the fascinating world of computer modeling and its essential role in both classical and modern physics. Imagine this. Newton, one of the fathers of differential calculus, painstakingly solving a complex equation by hand. It could take him hours, even if he had discovered that particular equation himself. Fast forward to today, and a computer can perform millions of arithmetic operations in mere seconds to solve the same differential equation. This astounding computational power is not just a convenience, it's a necessity, especially when we venture into the realms of quantum and relativistic physics. In classical physics, computer modeling provides quick and efficient solutions to problems that would otherwise be time-consuming. However, it's important to note that classical physics is essentially the macroscopic limit of quantum mechanics. As we scale up from a few particles to a large number, the probabilistic nature of quantum mechanics converges to the deterministic predictions of classical physics. On the other hand, classical mechanics can also be seen as a special case of relativistic mechanics. For example, in many formulations derived from special relativity, a correction factor involving the ratio of the object's velocity to the speed of light appears. When dealing with velocities much smaller than the speed of light, these correction terms become negligible. reducing the equations to familiar Newtonian mechanics. But here's where things get even more intriguing. Computer modeling must strike a balance between accuracy and computational efficiency. While classical physics can offer quick approximations, these solutions often lack the precision required for cutting-edge scientific research. Quantum theories, though more resource-intensive, provide the reliability needed for accurate predictions. In practice, physicists often start with a classical model to get a rough approximation. This initial model serves as a foundation, upon which more exacting quantum or relativistic models are built. The computer model then uses energy criteria to determine which theory, relativity or quantum mechanics, best describes the behavior of the system under study. Classical physics, as we've discussed, provides a macroscopic view of the universe, dealing with objects and phenomena we can observe directly. But what happens when we zoom in, far beyond the reach of our naked eyes, into the realm of the very small? Quantum mechanics, the branch of physics that deals with the behavior of particles at atomic and subatomic scales, introduces us to a world where the rules are vastly different from those of classical physics. Here, particles like electrons and photons don't adhere to the deterministic paths predicted by Newtonian mechanics. Instead, they follow principles that can seem almost magical. In classical physics, an object is in one place at one time, but in quantum mechanics, particles can exist in multiple states simultaneously. Imagine a cat that is both alive and dead, until someone opens the box to observe it. This is the famous thought experiment known as Schrödinger's cat, which illustrates the concept of superposition. Then there's a phenomenon Einstein famously called spooky action at a distance. When particles become entangled, the state of one particle is instantly correlated with the state of another, no matter how far apart they are. This means that a change in one particle's state will immediately affect the other, defying the classical idea that information cannot travel faster than the speed of light. The more accurately we know one, the less accurately we can know the other. This inherent uncertainty contrasts sharply with the predictability of classical mechanics. These principles of quantum mechanics have profound implications for modern technology and scientific research. Quantum mechanics is the foundation of technologies like MRI scanners, semiconductors, and even the emerging field of quantum computing. Quantum computers, for example, leverage superposition and entanglement to perform complex calculations at speeds unimaginable with classical computers. As we continue to explore the quantum world, we unlock new possibilities and deepen our understanding of the universe. The strange and counterintuitive nature of quantum mechanics challenges our perceptions and pushes the boundaries of what we consider possible. Thank you for joining us on this journey into the mysterious realm of quantum mechanics. If you found this chapter intriguing, make sure to like, subscribe, and hit that notification bell for more insights.